Hello, everybody. My name is Alex, and this is Alex Derives Stuff. The thing I wanted to share with you today is a geometric construction using only straight edge and compass, or, well, this is going to be a virtual version of straight edge and compass using GeoGebra. So I promise only to use the plot a point, construct straight lines through the points, and construct circles with a given center and edge. What's the particular one I want to do today? It's one of the earlier ones in Euclid. It's construct a line parallel to a given line through a given point. Now, the particular construction that I'm going to do today is not your standard construction for this. I believe something very similar to this is used as a later construction in Euclid to construct a rhombus. And as you'll see, like one of the things we get using this construction is a rhombus. Um, but I think it's a cool one, and I think it's better than the one, in my opinion anyway, it's better than the one that uses the angle copy algorithm that you usually see on this. It uses basically fewer things. The downside of this one is that it's less obvious that the line you actually get is parallel. So we have a given line. So let's draw a given line here on GeoGebra here. So there's a point A, there's point B. So those are 2 points on a line, and we're calling that line AB. And then we're given a point C. I'll just plop this somewhere up there. There's point C. And my goal here is, so I want a line that's parallel to the line AB that goes through the point C. So how are we going to do this? Well, first, we're going to construct circle AC. So my notation for this is that A is the center of this circle and C is a point on the edge of the circle. So to do that, so circle with center through point. So there's center at A, edge at C. And maybe I could zoom out a bit. There we go. So we could see the whole circle. You don't necessarily have to sketch the whole circle. You probably only need to sketch the side of the circle, or that, like the half of the circle that's on the same side of the line as C. But, we'll draw the whole circle here. Okay, so now we also want to construct circle CA. So again, with this notation, hopefully you're getting the hang of it already. The center is at C, and the edge of this circle is at A. All right, so center's at C, edge is at A. And I'll make this circle a different color here. So let's make it like blue. All right, we got a blue, so we got a black circle centered at A, and we've got a blue circle centered at C. And an important thing to notice about these two circles is that they have the same radius. So if I draw a line from C to A, so, right, like that line is a radius of the blue circle because it's one ends at the center and one ends at the edge, and is also a radius of the black circle because A is the center and C is the edge. So that means these two circles have the same radius, and well, that means that if I draw another radius of either one of the circles, that line will also have the same length. That's the great thing about circles. So we want to create a new point, D. Now, D will be the intersection of circle AC, so that's the black circle, the one with the center at A, with the original line, AB. You might notice that there's 2 points of intersection. Well, turns out we could pick either one. You can try this construction using the other point of intersection. Yeah, either one will work as it turns out. So I'm going to pick that one just because, well, it's closer to the middle of my picture here. Okay, so if we look at another line segment, segment AD, that is a radius. So that is also the same as the line segment AC. Both of those are radii of circle AC, the circle centered at A and edge at C. Okay, cool. All right. So we've got that intersection. So now, we want to draw another circle, circle DA. So centered at D, edge at A. And I will make this, I don't know, that color. Okay, I think that's pink. So centered at D, edge at A. All right. So we've got 3 circles, and this circle, since AD is a radius of this, and it's a radius of the black circle, then this circle also has the same radius as the other 2 circles. All right, so now what I want to do is look at, I need a new point, E, that will be the intersection of the circle we just drew with the circle that's centered at C. So this is the pink circle and the blue circle. Where do they intersect? Well, they intersect at point A. I don't want to use that one. We want to use the other intersection. So bang. All right, so there's point E. And then what do we do with point E? Well, we construct a line through C and E. So if we construct a line, so I'll do the full line that goes all the way through them, through CE, and there's our second line. And this line is parallel to line AB. Okay, so there's your construction. It's a pretty simple construction, right? You know, no need to like reset the compass or whatever, right? Because you know what all the points are and stuff like that. And I can draw more line segments here because that are all radii of a given circle. So CE, that's a radius of the blue circle. Yeah, DE, that is a radius of the pink circle. All right, cool. So, so this little orange quadrilateral here is a rhombus, right? All 4 sides are the same length. All 4 are radii of the circle. Now, here's the thing, is it's not necessarily obvious. I mean, it's not necessarily obvious that these lines are parallel. It's possible that they are a tad askew. So we need to, and then it's possible that if I did this some other, with some other orientation or something, that they might not be parallel. So what I need to do is I need to prove, in order to be confident in this construction, I need to prove that this construction works all the time. So how do we do that? So how do we know that these lines are in fact parallel? Well, okay, so we need to go back through Euclid's elements and pick out a couple of propositions that I don't want to reprove. We need to use alternate interior angles. So if the alternate interior angles of a line cutting 2 other lines, 2 given lines, are equal, so if the alternate interior angles are equal, then the 2 given lines are parallel. So interesting. The second one we want to know about is the so-called side-side-side congruent. So if I've got 2 triangles and all 3 side lengths of the triangle are the same, then the interior angles are also the same. So using just these 2 things, we can prove that lines AB and CE are in fact parallel. So how are we going to do this? Well, first thing we need to do is notice, and we've been talking about this the whole time, so all 3 of these circles all have the same radius, and that means that the line segments AC, AD, DE, and CE, they all have the same length. All right, so right, because each of those segments is a radius of, well, I guess what ED is only a radius of one of the circles, but it only needs to be a radius of 1 for these to be the same length. Okay, so now we'll take one that's not a radius, CD. We'll draw a line segment between those 2 points. So CD. So segment CD. And let's make this one a different color. Let's make it black. All right. All right, so now we split up our rhombus into 2 triangles on either side. And what I want to do is I want to show that these are in fact congruent triangles. So let's see, how are we going to do that? Well, this is side-side-side congruent. So let's draw some triangles here. So triangle CED. There's C, there's E, there's D, and then back to C. That triangle is congruent to triangle DAC. And oops, back to D. Okay, and let's make this one purpley color. All right, so what I've got here is triangle. Yeah, I've got 2 congruent triangles. Why is that? Well, CE is the same length as DA, right? So that's the first two letters. ED is the same length as AC, right? So that's the second two letters. And then CD is the same thing as DC. Oh, okay. So three sides are the same. The corresponding angles should be the same. So in particular, the two angles I want to look at are angles ECD and ADC. And we can label these angles with a little circular sector here. So angle ECD means the angle whose like for an angle, the middle letter is the vertex of the angle. And then let me get rid of the G there. Okay, cool. So that angle, that's angle ECD. And angle ADC. So I got to draw another little circular sector there. So D is the vertex, and it goes there to there, whoop, onto the line, and whoop, doo, doo, doo. So I know those two angles are the same because they are corresponding angles of congruent triangles. All right, cool. So, but these angles, if you notice, are also alternate interior angles of segment CD cutting the lines AB, that's the bottom line, and the line CE, that's the top line. Oh, so that means basically we're done. So by 127, the alternate interior angles thing, AB and CE are parallel, and we're done. So now we know the simple construction, which was basically like three circles, works to construct a parallel line. And I will say a few points in this construction's favor, and in this proof space, we needed the proof just to, well, to make sure that it worked, right? This one extends to finding out things like properties of a rhombus and doing all sorts of other things. So this is a cool construction. I hope everybody enjoyed all of that. Hopefully I'll be making more of these soon.